Okay, friends, on behalf of Center of Excellence in Advanced Manufacturing Technology at IIT Kharagpur, I would like to welcome you all in this mega webinar series, which we named as the Saturday Manufacturing Talks. So for the last 45 weeks, we are getting assembled 8:30 p.m. in the Indian Standard Time to listen to the various researchers across the globe talking about different fields in the advancement in the different fields in manufacturing. And today is the 46th week, so you can understand that the Center of Excellence in Advanced Manufacturing Technology, our researchers, faculty members, and the other the people across the globe, so they are getting an opportunity to interact with the eminent researchers. So today we are very much fortunate to have Professor Dragos Axinte from University of Nottingham with us. So I'd like to read a brief biosketch of the professor. Dragos Axinte is professor and chair of manufacturing engineering at University of Nottingham, UK. Graduated at University of Galati, Romania. After working in industrial research for nearly 8 years, he held 2 personal NATO research fellowships in Italy and Denmark, and then moved to the UK to carry out research with the University of Birmingham and later with the University of Nottingham. He was appointed lecturer in manufacturing engineering in 2005 and successively promoted to associate professor in 2007, reader in 2010, and professor in 2011. So you can see that very high rise, the achievement of the professional caliber. Since 2009, Dragos is director of the Rolls-Royce UTC in manufacturing and on-wing technology at University of Nottingham. He is editor-in-chief in International Journal of Machine Tools and Manufacture. We all know the standard of International Journal of Machine Tools and Manufacture, and fellow of International Academy of Production Engineering. Dragos has over 200 journal papers and over 20 granted international patents filed with industry partners. So he has got a very strong collaboration with the industries. Dragos' research interest is in the following main areas: advanced machining technologies, both conventional and non-conventional, and workpiece surface analysis, with particular interest on the changes of material properties caused by the thermomechanical loads resulting from the machining. So you can understand the very fundamental research Dragos is executing in the fields of the manufacturing. So today's topic is that time-driven manufacturing processes is very interesting. Why the inverse problems need to be solved. So let us all listen to Professor Dragos Axinte.
Thank you, Professor Surya, for your introduction. So kindly ask you for allowing me to share the presentation.
Ananta, please give access to Professor Dragos.
Okay. Okay, so everyone can see my screen, right?
Yeah. You can go to the presentation. That's right. Yeah, brilliant.
Okay. Thank you very much first for the introduction. So let's clarify. My name is not Professor Axinte. My name is Dragos. Yes. And today, I was in a bit in balance, a bit unsure what topic I should be presenting, because I looked at the history of what has been presented before. And I've seen some, my last topic is machining, but I have seen that other reputable researchers, they have made a presentation related to machining. So with the surface integrity and so on. And although that topic is more closer to my heart, I said, okay, let's change a bit the pace and try to attract the attention to the young generation or to our researchers, yes, a research community, to some interesting problems which might come from time-dependent manufacturing processes. And I will try to emphasize the need of solving the inverse problem. Probably from time to time, I might use a bit of a stronger language of criticizing why people have not been thinking about some topics, but that's how we should do actually a literature review. We should do a literature review with a critical eye, otherwise there is no progress. So my name is Dragos, and I'm also the director of Rolls-Royce UTC. Probably you might not know that it's University Technology Centers. The Rolls-Royce has over 20 research centers around the world, and we are one in focused on manufacturing on-wing technology. And I will make a short introduction. First, University of Nottingham, just to give you an idea. We are ranked number 8 in UK as a research power, and quite a good, you can see around 20% of the research comes from industry, and we have a good percentage of research considered at international standard. Probably you might say, who said that? Is the UK has a research body which evaluates us every 7 years. Actually, now we are waiting for the new research assessment exercise results to come out. Yes. Okay. So you can see I'm not I'm presenting my group. Actually, it's first we have Rolls-Royce UTC. It's a main source of collaboration. At the moment, we're running over 30 projects with a company. We get funding from EPSRC, which is our research council. We have been coordinating a couple of good number of European projects, which and also we get money from industry. This is a body which is called Innovate UK, and this is more applied research. So we have a mixed portfolio of research income. Yeah. Oops. And so just to give a bit of introduction, what we do under our Rolls-Royce UTC, we have been established more than 20 years ago. Actually, we are the only research center in the world which we have a full Trent 1000 engine for demonstration of our technology. So the picture you have seen here, you see here, actually it's a full engine. It's in our labs. Yeah. And what we do, we are based in the division of manufacturing. Actually, this is the new building we are in at the moment, and this is the group 20. At the moment, the group is over 40 people, and we have different strands, and which I'm going to present them shortly. So one is robotics for in-situ repair. So that's why our UTC is called manufacturing and on-wing technology. So just to incite you here, you can imagine that sometimes the inspection on very complex installation needs to be done, and some of them it will be very advantageous not to dismantle the installation. So imagine an engine on the wing on the aircraft. This is inspected at regular times, and if some defects might have been found, for example, a blade which has been probably distorted by hitting a small engine ingesting a small stone. Yes, this might be, the blade might have the airfoil a bit distorted. So there are particular procedure. This has to be blended, you know, so to that indentation removed. And for that, there are no such tools for this. So we are developing robotic systems for making in-situ repair of the aero engine. If you are interested, we make snake arms, and the most, let's say, advanced system, we have a 5-meter snake arm with 9mm diameter. So imagine a 5-meter snake arm with 9mm diameter. So these are kind of, and everything is done in-house in our lab. So that is one strand of technology. Oops. Next, we do innovative tooling and fixturing within the Rolls-Royce UTC. And why we do this? You can buy the most expensive machine tool and most performant cutting tools. But if you don't position the workpiece relatively to the tool precisely, or to the workpiece start vibrating, is not the best solution. So most of the people spend a lot of time looking at how to minimize vibration, for example, by adjusting the cutting parameters. But very few people they have been looking how you can do that from the workpiece point of view. That means the fixtures. So we have been spending more than 10 years developing innovative fixtures for the company. And we have also a group in a group of mechatronics. So you can see the robotics ties up very nicely with the mechatronics. Actually, we make systems which can get in situ of large structure to make repairs, and also end effectors. Because if you want, for example, to make deposition of a material, to give you an idea, for example, to make this in situ repair in the gas engine, you have some access ports which can be as small as 10 millimeters or less. So how you introduce there a tool? So you might have probably a snake arm, as I commented, but you need also an end effector which has to be small. So we don't work only on robotics, but also we work on mechatronic system and miniaturizing end effectors. Yeah, and of course we also deal with advanced manufacturing technologies, and we cover in our lab we have quite extensive equipment from 5-axis machine tools. That is okay. We have lasers from micro to femtosecond in our lab. We have 2 water jet machines, EDMs, and so we are very well equipped from this on this. But what we are somehow very different from most of the machining groups around the world. We do, and we have facilities in-house for advanced material analysis. So what we do is from SEM, TEM, focus ion beam, EBSD, TKD, all these techniques. Our guys, they do it themselves. We don't work with the material people, basically. Everything is done in-house. So what we make there, we make the link between manufacturing technologies and understanding what happens at the material level. Yeah. So, but the topic, so I was supposed to talk, actually I was supposed to talk about time-dependent processes. So now I want to give you, to start now, making you aware what I mean by time-dependent, yes? So let's consider an energy beam, yes, which can be an abrasive water jet, can be laser, and focus ion beam. Can you see? Actually, I'm presenting you 3 very different processes: water jet, laser, and focus ion beam. So they are totally different. So, but all of them, what they are? Nothing else than energy beam, right? And what they can have in common, they have an energy density, which we can probably measure, yes, by some means, yes. And we have time exposure on the surfaces. So these 3 processes, which I will carry them, yes, refer to them during my presentation. They are time-dependent processes. So let's make a comparison between a normal milling operation, yes, to emphasize what is a time-dependent, what will be the implication, right? And energy beam. If you start moving a cutting tool on a path, yes, if you still rotate the tool and you stay in one place, you stop, but still rotate the tool, the material is not removed. But in these cases, on energy beam, yes, you all the time, if you stay in that place or you accelerate or decelerate, you start changing the eroded material, yes? And now, again, imagine I have a tool path, which is a raster, let's say left, right, yes? Whenever I change the direction, I have acceleration and deceleration. Oops, so what does it mean? With acceleration and deceleration, you change the exposure time. And if you change the exposure time, you change the eroded material or the material removed. So very fundamental difference between planning a process or path planning for a conventional process, independent of time, most of them, yes, like material removal processes with the cutting tools, and those which are time dependent. And here, I think I will make a summary at the end, there are quite a lot of time-dependent processes, and the way, in our opinion, they are treated, yes, by our community, manufacturing, is somehow superficial. And I will give some good examples later on, yes? Oops. Okay, so again, I have a source of energy, yes, can be water jet, for focus ion beam, laser, pulse laser, I'm saying, yes. And I have a energy density, and I have a workpiece, and this is the footprint, yes. This is the material I'm removing, the white here, yes, I'm removing from it. And you can see here I have a velocity, V1, yes. Now, if I have the same source of energy, and if I change the velocity, for example, I'm getting slower, what happens? I remove more material. So there is a dependency of what? The feed speed. Actually, it's not a feed speed, it's the time, exposure time, yes? Exposure time. So what we see first, the depth, yes, of the penetration changes, but also the changes, what? The shape. So somehow people, if you want to generate now, of course, now with the change the feed speed, what I'm trying to say here, if you go very, very slow, what you can do? Cut the material. But if you start going a bit faster and faster, you remove less material. So changing, so what is the philosophy behind here? How I should be dealing with this process, with time-dependent processes, for example, with beams which remove the material. Shall I try to change the operating parameters like pressure pump for water jet? Shall I try to, or probably it might be better, because if you change the pressure, for example, on the water jet, what will happen? It will take some time. There is a time delay until from the moment you change the pressure to change the penetration of the jet, yes, or the footprint. It will be a time delay between the time you have the command and until the pressure changes. So actually you cannot generate very complex shapes by this, but it will be much easier actually if I change continuously the feed speed. So it's like cleaning the patio with a high pressure jet, yes. If I go slower, I remove more. If I go faster, I remove less. So what will be the strategy behind? Okay, if I change continuously in a way that I have a model behind which links me the exposure time with how much material and what especially what is the shape of the footprint, I'm in business. I can generate very complex shapes. Okay, that might be the first part of the story. But if you don't start from a flat surface, the problem becomes very, very complex. However, I would like to emphasize here a paradox. Most of the people, and somehow it's should be criticized. In the past, they said, oh, I have a model which will determine me the depth of the penetration. And of course, the depth of the penetration, it's useful, yes, of the footprint. But if you want to generate a complex shape, you have, for example, I have to go once with this feed speed in transverse direction. And after what I have to do? And come and have a step over, meaning the jet has to go sideways and go again. So actually, knowing only the penetration depth is not useful, because actually you need to know the whole, the full shape and see how this will overlap and which will be the resultant surface. So what I'm trying to get to here, there is an absolute need to know this shape, how this shape of the footprint, yes, of any energy beam, yes, in this case for removal the material, looks like when it's dependent on the time. And we will give some hints how this has been done, yes. We have been publishing for more than 10 years about this topic, yes. So I think the motivation, it will be, is very difficult, yes, to generate free forms by, for example, water jet, laser, pulse laser. So pulse laser, I have pulses and I remove material and I have to superimpose these pulses, and also for focus ion beam. And we develop a modeling framework which can address these challenges. And we proved that we published in Science Advances some 4 years ago, this topic, yeah. So here is more or less for the show. We wanted to say that these three processes are complementary, and I will go a bit fast here. Dimensional accuracy, of course, the water jet you might not obtain very precise surfaces, and what one process can do, the others cannot do. For example, this is require focus ion beam, will require vacuum. This one cuts any material. And anyway, I'm going faster here. The motivation, yes. But what I want to bring you this. why do we need this model? So why we should not be possible to just try different parameters and error and trial and so on. And here I'm presenting you actually with some results of one of the projects actually with one of your colleagues from IIT Madras has been doing with us nearly 10 years ago. Yes, Dr. Srinivas Devadula. Yes, we did some milling on silicon carbide composites, titanium 6-4. So you can see they are quite simple features, right? This is a pocket. This is a pocket and composite material. Here it's a ramp surface, a conic, yes, and a frustrum and a hole. And how we generated these surfaces, we tried different paths, beam path, yes, and try to adjust the cutting, the parameters to switch on and switch off the beam, yes. And actually, I should have taken a piece of paper. Oh, just one sec. Just one sec. Oh, I should have taken a piece of paper. Just one sec. Let me see where I have a piece of paper. Okay. Yeah. Good. Just wait for me. Yeah.
Yeah, sure.
How these surfaces are generating? Look what I'm doing, guys. This is a Christmas card. I'm destroying a Christmas card. Yeah. Look. Most of the people, when they do water jet milling, they don't tell you what is their trick. Actually, they have a mask. Meaning, I want to generate this pocket. What they do, they take a piece of sacrificial material. They make the machine the hole here, which they want to machine. They put on the top of the surface. And after that, what they do, they start rastering, yes, the surface. They want to generate a simple pocket, yes? So can you see, they go with the jet one direction, for example, make a raster, but where they reverse the jet, they reverse on the mask. Why they do that? Because whenever, as I said, whenever you reverse the jet, yes, you change the direction, you change the exposure time. If you change the exposure time and you have there an over erosion, all these features you can see here, they are done without the masking, meaning we try to optimize the path in such a way that you don't stay more time in one place than in another. Yes, so it was more by intuition. It took us probably 2 years to come to these surfaces. So you can imagine that it's not the most efficient way to do it. Okay, come on, go. When it came to pulse laser ablation, we had some ideas. So here, what you see, some pictures of ablated surface on titanium diamond structures. What we wanted here to generate some abrasive tools, we control shapes, yes, with control shapes of abrasives. Once again, we move here the beam without any modeling. It took us some time to arrive to these shapes. Oops. Sorry. Okay. I see something here and I'm moving. Okay. So what I'm trying to convey is not rational to try different parameters. So what would be so long tedious time, it takes a lot of time to adjust the parameters to move the beam intuitively, yes? So I'm going faster here. So what is our generic approach? Let me try to explain to you what is our generic approach. So first, d zeta dt is the variation of the footprint depending on time. And here what we have a generic etching rate or erosion rate, which depends on the time and the current surface. So we don't start from a flat surface, and the initial position of this. And after that, what we have here, we have a vector parameter, meaning what is the energy across the beam. That means the density distribution of the beam, yes, which we characterize. But what is this element here? This is the 3D path of the beam. So this PT includes the path, yes? So what is the direct problem, yes? Okay. What we observe here now, this I will show later on that this erosion rate ends up with a very difficult differential equation. which cannot be solved very easily. So what we observed, that if you move the jet very, very fast, yes, very, very fast, actually you generate a very shallow trench, very shallow footprint. That means the problem can be linearized, and you will see the advantage. So let's have a look here at what I'm presenting. On one side, you have the path parameters. Here you have the surface, yes? And you have a kind of a model which links the path with the surface, right? Good. So look, this is the direct problem. How people do at the moment, yes? They say, okay, actually most of people don't have a model here, but they might have FE problem, let's say FE model or a kind of analytical model, which leads me link the path, the beam path, which also include the path, the kinematic parameters, kinematic meaning the jet trajectory, its orientation in space, as well as velocity, yes? So this is the path. And here I obtain a surface. So how much, most of the people, they do, okay, I will decide this is the path, yes? They decide the path. And after that, they say, okay, let's hope I get the surface. But we will show later on that this is called the direct problem. I decide the path, and let's see which is the surface. I might have a model which can be precise, and I will get some surfaces, but the surface is very unlikely to be very obtained with very small errors. However, the real problem here is the inverse problem. Yeah, why it keeps on? Okay, the real problem is the inverse one. So would be actually not real to say, okay, I want this surface, tell me which is the the beam path. So as far as I'm aware, most of the people, they have done the direct problem, yes, with different kind of model here. But actually the real problem is, tell me I give you the surface, tell me which is the path, meaning which is the direction of the beam, yes, which is its orientation in space, and more than that, also velocity. So this will, we will show it later, that this doesn't need necessarily to be linear, because most of the people, they say, okay, go left, right, left, right, left, right. But why? Probably there is much better way to move the beam to obtain a particular surface, and we will prove that, yeah? Okay, so forward problem, it's clear, yes? So exactly what I said, you have this is an example on water jet. We have a jet which has a path, which has to follow a path with a particular orientation. So first we try to solve the direct problem, because if you solve the direct problem, then you will try to address the inverse problem if you have the equation there, yeah? So this is to keep it very somehow simple, this is the footprint. This is the footprint here, depending on time, yes, which depends, yes, dependent on time, which will depend on the orientation of the jet and also of the etching rate. So what we mean by this etching rate? Okay, let me make it very clear here. As I said, I gave you the hint at the beginning. Probably it might be, it is more practical. Look, can you see here? What parameters I'm keeping for the water jet, for example, constant. I'm keeping pressure. I think it makes sense, because if I change, I cannot change the pressure very fast in the pump. And even if I change it, these changes will not be, it will take a while until it comes here at the exit of the velocity of the jet will change at the exit of the nozzle. I'm keeping constant the abrasive mass flow. This is also makes sense, because it will, for the same reason, it will be a delay from the time I'm changing the mass flow of the abrasives. So I'm keeping constant the orifice diameter, nozzle standoff distance. So what I'm varying, I'm varying feed speed, I'm varying orientation and jet path, the path direction. So I'm changing the feed speed and the orientation and also the feed speed. That means the feed speed is nothing else than the time. And this is a pretty nasty non-differential, non-linear differential equation, which can hardly be solved. But what we introduce here, and I'm explaining this is an etching rate. So what does it mean, this etching rate? Etching rate is, I'm keeping all these parameters constant, yes, for example, and I have a set of what? Keeping these parameters constant for a particular workpiece material. Okay, so does it make any sense to keep them fixed? Yes. Does it make any sense to change these parameters? Yes, because this one I can change them very easily via NC program. So I'm changing the path, I'm changing the exposure time. So it makes sense to do it in this way. So the etching rate, I don't care about the physics by which the material is removed. I don't care. All this physics, it's introduced in this etching rate. Now you might say, okay, how I calibrate the etching rate? As we said, if we move the jet fast, and if I move the jet fast, for example, what I will have, this trench will be very, very shallow. If it's very, very shallow, the equation, this differential equation can be linearized. Okay, so if it can be linearized, what is the advantage of it? Let me explain to you. What we don't know here, we don't know the etching rate. We said if I go with the jet very, very fast, this footprint will be very shallow. I can linearize the equation. So what is the advantage of linearizing? I can actually obtain this etching rate. So let me explain to you how we calibrate the whole process. First, we keep the parameter constant. What? I will keep the pressure, mass flow of the abrasive, and all the other constructive elements of the water jet. Diameter of orifice of the focusing nozzle and so on. So what I will do, for that particular material, I will make a trench, yes, and I will scan it. But trench, I will make it with a very fast feed speed. So what will be the advantage? The footprint will be very, very shallow. Therefore, now, if I have the footprint, so now I scan the footprint. If I know the footprint, what I can do? I can calculate the etching rate from here. Yes, I want to give you, yes, this is the footprint. So I want to get this etching rate. So the whole idea behind it is I make a single footprint, a single trench with a high speed. I linearize the equation. I scan I scan the footprint. If I scan the footprint, I know the shape of the footprint. So therefore, I can calculate the etching rate. With the etching rate, after that, you can predict. Let me go back. If I know the etching rate here, after that, if I change the time, meaning the velocity, I can calculate how this trench will change with different feed speed. So it's exactly what we prove here, that with the calibration, yes, for the etching rate, we start after that changing different velocities, yes? And after that, okay, you remember I said that if you do, as people have done in the past, you know, they said, oh, I have a model which will give me the maximum penetration depth. That is not of any use, because if you want to generate a surface, you have to overlap the trenches, right? So now what we have see here, jets with different overlapping, and how the simulation comes closer to the real experiment, of course, with the noise from the measurement, yes? Here you have a very simple surface, a flat surface. We try to calibrate it to see if for a particular level of overlapping, how well our model is able to predict the surface. This is in titanium 6-4. So once again, what is the principle of this one? I include all the physics of the material removal for a particular energy of the jet, meaning pressure, in this case for water jet, yes. And I calibrate this etching function. If I calibrate this etching function, I can use that generic formula, which takes into consideration the time, how the jet footprint varies with the time. Okay, so that is for the water jet. I will have some proofs later on of more complex surfaces, but okay, so the first example for this dwell time or time-dependent processes was water jet. Another one is laser ablation. Yes. So what we do here, we have a pulse, a series of pulses, right? And here you have a footprint, for example, in diamond, and a footprint in titanium 6-4. Yeah. So if I want to generate a complex shape, you know now that for maneuvering the beam, yes, I have the pulses here of the laser, yes, and it's, I remove and I have the same, a footprint here, yes. And if I want to maneuver this beam, yes, how I do, I have a galvo, yes, which is a 2D galvo, meaning I have a series of mirrors which will scan this beam across a particular path. So I have a series of pulses, yes, and each pulse will remove the material, yes. So initially, I will make the story short here. Initially, what we have done, we try to model the surfaces you try to obtain, yes, by a series of pulses, individual pulses. So I say, okay, I have a pulse, yes, I have a pulse, I model a pulse, yes, or a footprint from a single pulse. And after that, I try to overlap them. You can see I have a pulse, we calibrate in the same way, we scan it, we see the etching rate, and after that, what we try to overlap it one by one, yeah? Now, going back here, you can see the scale of this one is 20 microns, for example, yes? So it's 40 microns, 50 microns, okay? 60 microns here. Now, if you want to generate a surface of millimeters, you can imagine how many pulses you have to simulate. You have to simulate one pulse, another one, yes? So it's basically what we say here, yes? Simulating and overlapping the pulses, yes? Here, here the model has been verified only on linear trenches. So we said, okay, this might look okay. Pulse by pulse, yes? Nevertheless, the situation becomes even more complex if you don't have a target surface which is flat. So here with the same pulse by pulse, we try to simulate what happens, how is the resultant surface, simulating pulse by pulse, yes? Remember, we are still talking about forward problem, meaning I decide the path, I know how it's the pulse, the footprint, and I overlap these footprints along the path and say, okay, I hope I will get a kind of, you can see here, it's a kind of satisfactory prediction. But this is a very simple path, right? It's a linear path. Of course, here I have some noise from the material redeposition because titanium 6-4, yes? And here it's an example of a surface and error 10%, more than 10% between only a flat surface, right? So the strategy here again was simulate pulse by pulse. You might need to simulate this convolution of a single pulse, you know, along the path, probably millions of them, yes, which is computationally expensive, yes, and probably. And you can see also is not generating fantastic prediction. It's on a flat surface, right? So, but we had after that we were thinking, actually, do I want to simulate such a thing? Meaning pulses which have a very little overlapping, yes, but pulses with very little overlapping do not generate a smooth surface, right? So if I have a big distance between two pulses, yes, they have an overlap, but you can see here, I go back on purpose, yes, if here you can see it's wavy, yes, and we did this on purpose because we wanted to calibrate the model. But if you come closer with the pulses, what you will obtain? Actually, you will obtain a trench. So we were thinking, oops, if we want to simulate a trench, is more or less the same as a water jet. Why should be simulating pulse by pulse? I'm interested to generate smooth surfaces. If I want smooth surfaces with a pulse laser, what I should be doing? I should be trying to simulate trenches with the pulses, although they are individual pulses. So here, once again, we came with the same idea. we say, okay, the trench, which the footprint of the jet, which is resulted by many these individual pulses, but with very little overlapping, so it comes a smooth trench, so more or less like water jet, yes, for example, yes. What I have an etching function which will depend on pressure, on the power, feed speed, yes, and the path, yes. And what we have done here, actually, we said this etching rate, remember, this etching rate is nothing else how the material, in this case, reacts to particular energy of the laser, particular standoff distance. And here what we wanted to say, okay, this etching rate, which depends on the power, feed speed, that means exposure time, and radius, yes. What will depend? It will depend on the how this depth, yes, the depth of the trench will depend on the feed speed, how the trench will depend on overlapping, and how the trench will depend on the width of the overlapping. So what we wanted to say here, we separated this etching function in one which depends on the power, one only depends on a generic shape of the profile. So what we do, we have 1, 2, 3, 4. So we have 4 unknown for calibrating this etching function. So what we have done here, again, we did some trenches with a fast speed, we scanned them, and after that we have to make 4 trenches because we have 4 unknowns, yes? We make 4 trenches at different powers. And after that, what we do, we calibrate this parameter, alpha, beta, R, and etching rate, yes? So with this one, you can see this is a calibration, yes? This is experimental versus modeling on a diamond material. So this is the 2 footprints. Oops, but now, look, this is with a 0 overlap, now with more overlapping and less overlapping, yes? So meaning overlapping, I make a trench, and after that I go sideways and do another trench. Okay. So after that, we said, and I will show you later on, using this direct problem, forward problem, we start manage to generate free forms. And you can see here a logo from the European project, milled on titanium 6-4 with a direct problem, yes? And here on 0 dur, some surfaces, these are spherical glasses, and here it's in nitty material, yes? And after that, we use this model, the forward problem, yes, for laser ablation to make even more interesting features. So what you see here, it's an abrasive element, which we published many years ago. It's an abrasive element. We started from a flat piece of diamond and we start ablating the material around. So you can see all of them, they are identical. All these teeth are identical, yes? You can see here, look, it's 20 micrometers, you know, very small. And after that, small grinding tools in diamond. So we use these models to generate shapes of controlled geometries. Good. So up to now, we discussed only about forward problem, meaning I say, okay, I find the relationship between how the footprint of the removed material, the jet or energy beam footprint varies of what? Time and the path, yes? And how we said, okay, this is the path, and this is the surface. Yes, this is the surface I obtained. But actually, the real problem is the inverse one. Meaning, I tell you which surface I want, tell me which is the path. Before we decided the path, and after that, we, based on the model, we predicted which is the surface. Okay. So let me explain roughly what is the principle of this. Yes, this is once again is the surface. Yes, I want to obtain. Here is the etching function, and here is the path, is the dwell time. Yes. So we realize that actually we can instead of working in time domain, we can work in frequency domain. So we can apply the convolution theorem. So Z is the footprint, yes, or the surface I want to obtain in frequency domain, yes. This is the etching function in frequency domain. Dn is the tool path, yes, in frequency domain, yes. So what is the principle here? How we do? If, yes, I know En, yes, it's an etching rate. I told you that we can calibrate the system to find the etching rate. So I obtain the etching rate, and after that I transform it in the frequency domain. After that, Zn is the given surface. Okay, this is the surface I want. What I have to do is transform it in N domain, yes? And after that, what is this? This is nothing else than the toolpath, which I want, yes? So basically, we will obtain the toolpath here, yes, from using the convolution theorem, okay? So what is the implication now? Let me make a comment. Now, you have a water jet machine. It's generating a jet, yes, and this jet will erode and remove the material. So what I have to do, imagine now I start moving the head of the water jet, yes, on a particular path. But the head of the water jet, it's probably around 400 kilos. So now if you start moving left and right, yes, it's impossible that the dynamics of the machine, meaning the delay on machine executing particular moves with a particular acceleration. What will happen if I have a variation in acceleration? Yes. Means in the exposure time, what I will have? A variation of the footprint. Compare with the laser. In laser, what I'm moving? Yes. What I'm moving in the laser? I'm moving nothing else than a mirror. So I will have a much better response on the laser machining compared with the water jet, because I have less masses moving around. So what I'm trying to hint here, we have indeed a tool path, yes, a path, yes, dwell time, yes, let me go back. I can obtain this one in frequency domain, and after that transform back in the time domain, yes. I can, what's wrong? Okay, I can have this one, but actually the path, if I put on a system which is like water jet, where I have big masses to move around, the machine might not execute exactly the velocity, might not be able to respond exactly to the path you are asking. So here it's an example. What we did, we tried to move continuously the water jet, yes, on a particular path. So what you can see, this is the desired trajectory, which comes from our previous model, yeah, which I showed on the previous slide. And this is the measured data. So why the difference? Because the masses involved in moving, yes, movable masses, you know, which gets the jet head, you know, will influence the machine dynamics. But of course, you might say, okay, you might know the transfer function of the machine. No one will give you the information because it's a proprietary from the machine tool builders in the controller. So what we have done, we try to inverse, you know, to get derive, yes, experimentally the dynamics of the machine for a particular feed speed. So what we have done, we introduce in the machine different functions. So they say, okay, you go from impulse. So you go from this velocity, change that rapidly. So we have seen how the machine reacts. And after that, we ask the machine, go with a continuously increased feed speed, or go around the corners, you know, in this way, or make a sine function. In this way, we were able to find out how the machine responses to particular stimuli. And that's why we built here Hn, which is another function, which is a frequency response function of the machine. Not very precise because we didn't have it from the controller. No one will give you this information, but we try to compensate for these errors on the machine moving exactly where we want because of the dynamics. Of course, now on such a function here, correction function was not needed when you deal with the laser, because the laser you move only some 2 meters, yes. So they are very small inertia. So, and here what you see is basically what I just said. After that, we replicate, we ask the machine to move once again on a particular path, and we have seen the machine replicates well the path which we wanted. And after that, we said, okay, let's try first a frustum. And you can see here the frustum we generated with the laser machining in this case. But actually, I wanted to come to these pictures. Yes, here. You can see now with the inverse problem, actually, is much more precise. We could generate a very smooth surface, yes, with the logo of this one. I can play the video, but I think I still have some slides to go, so I will move faster. And actually, I want to stop here on this picture, which proves this is we published in Science Advances some years ago, this paper. So you can see here a feature. Yes, we could generate different features with different three processes, but we know for science journals, they don't want to see, you know, cutting tools and so on. So that's why we decided on Mona Lisa. What we have here, this Mona Lisa has been machined. This is with water jet, this is a pulse laser, when this is a focus ion beam. All of them based on the same principle on the solving the inverse problem, yes? And based it on the same idea. I have an etching function which I calibrate. The rest is where all the physics are included for that particular duo, yes, for the particular coupling between the particular beam energy and particular material. So what I need, again, I do some trenches, calibrate the etching function. And after that, you can see here A, B, C, and A, B, C. And you can see the errors, you know, how small they are. Look here, we are talking about how many millimeters? Over 30 millimeters, 35 millimeters by 35 millimeters square, with a machine which is has the head in excess of 500 kilos moving around, yes, and pretty low errors. And now if we go smaller for the laser, you can see this is 2 millimeters by 2 millimeters, very precise. The errors are very, very small. Focus ion beam, even smaller. So what we wanted to say, that previous pictures, which I showed you at the beginning of the presentation, were generated only a frustum, yes. It took us nearly 2 years, you know, to try to move the beam, change a bit of this, change a bit of that. The real problem to be solved in time-dependent processes is the inverse one. Is not you define the path, and after that, let's see, based on some model, what comes out. Good. So here are some examples also from the same science paper, you know, how we generated small surfaces. And you can see the beam actually doesn't need to go raster, left, right, left, right, left, right. Yes, the optimization method will come with the beam path, which is not necessarily linear. That's the whole point. And I will show, but okay, and I will give you an example of other processes which should be treated properly, meaning should be treated with the inverse problem. And let me show you a paradox here. Yeah, people talk about laser assisted machining. Okay, fair enough. So what is the principle of this? With some source of energy, yes, for example, laser, I come and heat up the part, right, in the front. And after that, this cutting tool comes in a softer material, removes the material easier, right? Yes, this solution is very, very convenient, and you can publish a lot of papers, but it doesn't have too much science in it. Let me explain to you why. If you have the laser beam more or less the same diameter with the tool, the process might still work, right? But look how the heat induced in the part looks like. It's not uniform, right? So, okay, but it still might work if the beam diameter is more or less with the tool diameter. But if the tool is much bigger, yes, if I have a tool like this, look like my cup, you know, tea cup, and I have a beam in front, yes, look, it's not very advantageous to hit it. Some people say, okay, I might raster, in front of the cutter, the beam. Actually, what we would like to have in front of the cutter a heat distribution or a temperature distribution like this, not like this, right? And how you obtain something like this? By error and trial. So once again, what we have done here, this was a European project which we coordinated. We have a galvo here, which will scan in front of the part. How we scan it? By solving the inverse problem. So what is the inverse problem? It's nothing else than the known thermodynamic equation, which we have a dependence of the temperature on the spatial, on the heat source, and here is the time aspect. So now, once again, what I'm interested here? I'm interested in finding the inverse solution, meaning don't tell me in advance how I should move the beam. I tell you which is the temperature distribution I want, which distribution in front of the cutter. So here will be the cutter, right? Here it will be the beam in the front. I have to move the beam in such a way that I obtain as constant as possible temperature. What does it mean? That probably the beam path, yes, has to be optimized in the front, yes, beam path, or probably beam path and the speed as well, yes, to be varied. So here you have an example of optimized solution. This is without optimization. Of course, here where you reverse the beam, yes, left, right, yes, you start building the temperature. So it's very unlikely you obtain a constant temperature, yes. While here, what you see, we optimize the speed. So basically what we did, we said, okay, I want an arc, but change all the time the speed in such a way that the temperature is constant. So again, what was the necessity? First, if I want to use for laser assisted machining, I have to move the beam in the front, but how I move the beam in such a way to obtain constant temperature, yes, at a particular depth, So this is the chip thickness, and I want the temperature to be a particular value, and in this case was at Inconel 708, and we know when the gamma prime it gets into solution, and meaning the gamma prime, which is strengthening a phase, it will go into solution. So we know which is the temperature. It's around over 700 degrees, yes. So we wanted, okay, in front of when the cutter comes here, you hit here, yes, but when the cutter comes exactly in this point, what will happen? I have to have 700 degrees, yes, over 700 degrees at this chip thickness. So the material can be removed easier, yes. And how we did it, again, we solved the inverse problem in this case. And in this case, here is presented the speed optimization. You can see the speed is varying during the path. Is it possible? Yes, because the galvo, it's very, very time responsive. And here you have an example of so we have an infrared camera here. And here what you see this is the milling cutter. Let me see the camera. Yes. Here it's a single spot. Now I sweep the spot, the laser, and after that I switch it off. So what will happen? Here I have a single spot in the front. Of course, it's not doing anything because the cutter is big diameter. I think it was around 30 millimeters diameter. And while the beam diameter is around 2 millimeters. So it's not doing too much, yes. And of course, here what I overburn the surface, burn the surface, yes. And so stationary spot, sweeping the spot, and after that the laser, and after the switching off. And what you can see here, of course, you can soften the material and remove the chip easier. The real problem here is actually when you want to decide on the beam path is the inverse one. Try to, given the path, the surface, tell me which is the path. Don't decide the path and after that see what is coming out. That is what I wanted to say. Sorry, it's 1 hour.
Yeah, thank you, Dragos. It's a wonderful session. and you have given us the insight about how the the inverse problem in the time dependent manufacturing process can be solved. You have given examples of the abrasive water jet machining and the laser based process, and also the iron wheel process. And you have rightly told that for inverse problem, the most critical thing is the optimization of the process parameters, given a for a given surface to be produced and all. So you have shown the example, the difference between the with optimization and without optimization examples and all. Just one question coming up in my mind
Yes,
before.
please.
Yeah. So before I proceed to my the friends participants who are over there, and I'm pretty sure some questions will be coming up in their mind as well. The how do you consider the material inhomogeneity when you are coming up? Your inverse problem is defining the some with the tool path and then other process parameters to be followed and all, optimizing the other factors like the dynamics of the machine itself, the total machining time, energy consumptions, all these things they are being considered. So how do you think the material inhomogeneity can be tackled?
Sorry, how?
How do you consider material inhomogeneity when you are solving this problem?
Okay, so how this originated? Actually, we had an European project.
No, how the material inhomogeneity?
Inhomogeneity. No, okay. We are working on this problem on let's say in this way. If the material is theoretically homogeneous, we don't have a big problem, yes, on this. Basically, I have not presented here. For example, we also have treated the aspects related to material redeposition, yes, in laser. But the errors, yes, probably might increase with a material non-homogeneity. And I give you an example now. We are working trying to solve this problem on obviously non-homogeneous materials like composite materials. And I think our methods will have much bigger errors like the bulk materials. So I don't think it's very easy to consider when the materials are obviously non-homogeneous. I don't think the method will work.
Yeah,
because you have different erosion rates, or different etching rates or deposition rates for different material. I don't think it will work.
Yeah, that's what I was wondering. That
Very good point. Let me tell you, we had one paper which we published in the journal related to pulse laser ablation of ceramic matrix. Apologies, on stabilized zirconia, and so basically we wanted to control the beam to remove layer by layer the thermal barrier coatings, and we established etching rate for one layer, another etching rate for the bond layer, so top the layer, bond layer, and the base material. But if the material will be intertwined, I don't think our method will work, because the etching rate cannot capture the physics. It cannot capture the physics of removing with the same beam energy two totally different materials. So if we talk about theoretically homogeneous material, we have not encountered any problems. We have done Inconel, it's titanium 64, diamond, ceramics, no problem. When you start probably going to metal matrix composites, I will have a problem. And I don't want to describe more other application because it's work which we are working on. It's not likely to work very well. Probably you should try to average the etching rate, which is not probably the best solution, and is not likely to get to the real.
Another question similar to that, for real, the application, when you are, you want to measure in real time, then if you face any difficulty, then how your inverse, the solution take care of the dynamic situation. Like
exactly. Good point. We at the moment, if you have the bigger the inertia of the system, the more there is the need for us to reverse engineer the dynamics of the machine. And I gave an example with a water jet because it has a 500 kilos head, with the whole, it's a gantry machine. It's a huge machine moving. Yeah. So what we did, again, we include different functions and try to see how the machine responded in a particular feed speed intervals, because from our simulation, we knew that the machine has to change the speed from this speed to V1 to Vn, yes? And after that, what we start doing, we start inputting different functions in the machine to see where we wanted the machine and where actually the machine was going with tracing the position of the machine. And after that, we corrected. Why? Because the machine tool builder will never tell you the inside of their controller. Nevertheless, on processes where the beam is less affected, the beam movement is less affected by the dynamics, for example, the laser, where you move only some mirrors, we didn't have a big problem, yes, to implement. So the dynamics of the machine indeed will influence a lot. So if you want to do laser cladding, for example, by the same idea, yes, or shot pinning, for example, yes, for example, with the pellets, with the shot pinning, probably you have to calibrate the dynamic of the robot or whatever machine you are using for moving the beam.
Okay, Dragos, some questions from the participants, like Ananda that has asked some questions. Like, first of all, everybody is appreciating your work. I must say that. And so he has raised, like, for a curvy surface, non-flat surface, do we need to adjust the angle of action? And
yes, yes. We change the attitude of the beam, yes, because for example, on the water jet, we have the possibility to tilt, because the water jet, it's a 5-axis water jet, and we adjust the position of the beam. It's this one, yes. Let me continue. For the pulse laser, we have everything on the, where is the picture? Because we have an aerotech system. You can see here, this is the galvo with the 4 axes underneath. So we change also the attitude in time. Clear?
Yeah. So another question from him is that you have given some example, nice example, the Mona Lisa, the print and all. So he has asked, like, for such micron level machining, doesn't the vibration of AJM cause any deviation? Is it considered in the simulation?
The vibration of the system, this is exactly what we try to do here. Not the vibration, is the dynamics. So basically, we know how the machine reacts, So the vibration, of course, the vibration comes, I'll give you an example. The vibration, the influence of the randomness of the system, it comes on this kind of footprints. That's why you can see when we do this kind of trenches, we are trying to, of course, now the trench is not constant, is not because of the vibration, of course, but the randomness of the process. So indeed, there are some variations, but what all these surfaces, which I showed here, they are based on average values, You can see this is that's why we present it in this way. Yes, indeed, on the bigger the masses movement, the more the dynamics will play a role, vibration or whatever.
Yeah, actually, the dynamics has to be, considered for all such process parameters, and more important for the inverse solutions and all. And the another question is, it's from Pooja. So she has asked, like, how do you keep the desired material properties intact while performing the reverse problem?
So I don't understand. Again, the materials intact? I don't understand. What do you mean by?
So, you know, the material properties does change as the process goes on, like the temperature.
That's a good question. That's a good question. Let me explain. For water jet, the material properties do not change.
Yeah.
Yes, because it's a removal the material with no heat. Yes, but on laser it changes the reflectivity. Yes, absorbability. We took that into consideration as well. You know, so we calibrated this. But calibration.
But at the same time, you know, the just analogous to this, the question is that at the same time, you know, the heating area is also going to get changed with the process parameters. So do you also take into consideration of the profile of the material erosion or the material change of the?
Yes, that we for the laser ablation, for example, pulse by for the trenches, we considered how the changes of reflectivity and absorptivity, all this laser material interaction will change from the trench to another one. We published just in our journal some 2-3 years ago. But on other processes like water jet, there is no need because you don't change the properties of the material.
So Dragos, it's a wonderful session that we had. It's a wonderful lecture as well. And a lot of people have asked, you know, shown interest in your work. And we'll, you know, look forward to work together in near future. Thank you so much for your presence in our Saturday manufacturing talk. And yeah, so I'd like to request Ananta, could you please let us know the speakers for the next week? Thank you once again, Dragos.
Yeah, thank you very much. It's me thanking you. Good night to all of you and all the best to you and your families.
Thank you so much. And our next speaker for the 29th of January is Professor Swaminathan Gopaliswamy. So he'll be talking about the health monitoring for cyber physical system.
Good. I will leave you guys there and all the best. And we can link Professor Surya. We can link. You can send me an email and we can fix a link.
I'll do that one. I'll definitely do that.
Thank you very much, Ananta, for your help and all the best to all of you guys. Thank you.
Thank you so much, Dragos, for your presence over here.
Thank you. Thank you very much. Bye-bye.
Friends, you can scan the code to get the past webinars. All webinars are getting recorded and put in the YouTube. With this, I'd like to close today's session and look forward to your presence on 29th of January. Thank you so much. Bye-bye.